This video will show you how to use PyTorch Contiguous operation to move a PyTorch Tensor's data to a contiguous chunk of memory. First, we import PyTorch. Then we print the PyTorch version we are using. We are using PyTorch 0.4.0. Next, let's create an initial tensor without specifying what the values are. We print the PT initial matrix Python variable to see what we have. We see that it's a tensor, and we see that it has basically just garbage values. So these are all placeholder values. We have no values in the matrix yet. Next, we use the in-place fill operation, so .fill underscore, to fill our tensor with the values of 2. So we say PT initial matrix .fill 2. Then we evaluate it. Note that we don't assign the result to a new Python variable because we're using the in-place fill operation, so it just fills in the values in the same memory that was initially allocated by the torch tensor operation and then assigned to the PT initial matrix Python variable. So we can print the PT initial matrix Python variable to see what we have. And we see that it is our matrix that has been filled in with the number 2's. And even though we know what size we initially wanted, we wanted a 5x3 matrix, let's check the PT initial matrix size by using the PyTorch's .size operation and we print the result. And we see that it's a torch size object that has the values 5x3. Let's now transpose our PT initial matrix Python variable to start exploring what happens to the memory where the tensor is stored. So we say PT underscore initial underscore matrix dot t. So that's the PyTorch transpose operation. We're going to assign the transpose matrix to the PT transpose matrix Python variable. We print the PT transpose matrix Python variable to see what we have. We see that we have 1, 2, 3 rows and 1, 2, 3, 4, 5 columns, whereas before we had 1, 2, 3, 4, 5 rows and 3 columns. So our matrix has been transposed. The one thing to note, and which is what this video sets out to show you, is that to save memory, PyTorch has not created a new memory location for the PT transpose matrix. It's still referring the initial memory location set aside for the PT initial matrix. The way we can see this is when we try to access different parts of the tensor. So first, let's access the last element of the first column of the PT initial matrix, so 4, 0. Again, remember that Python is a zero-based index, so this 4 means the 5th row, and 0 means the first column. When we do that, we get 2, which is expected. Next, because we know that PT transpose matrix and PT initial matrix share the same memory, we can try to access the same element. But this time, rather than using the PT initial matrix, we're going to do PT transpose matrix. 4, 0. When we evaluate that, we get the error. Index is out of bounds for dimension. So what that means is that PyTorch is checking to make sure, well, this matrix has 3 rows. How on earth are you checking for a 5th row? That doesn't make any sense, so it says index is out of bounds. That's great. What will be surprising is that let's try to flatten the PT initial matrix by using the PyTorch view operation to reshape the matrix into a vector using the -1. So we say PT initial matrix dot view -1. So we're going to take this matrix, the initial matrix, and we're going to flatten it. When we do that, we see that it's a tensor and there's a comma here, so it's one long vector of just 2's. That makes sense? All right, we get a vector. We can check our initial matrix to see if it's still the same. It's still the same. So the dot view operation does not replace our initial matrix. It just returns a new vector. Let's now try to flatten our transpose matrix. So our transpose matrix was 3 rows by 5 columns. Given that we transposed it, one would think we would be able to flatten it into a vector. When we do that, we run into a big error. The error reads, invalid argument. View size is not compatible with input tensor size and stride. Call .contiguous before view. The reason this error comes up is the way PyTorch stores the tensors in the memory location. The PT transpose matrix still references the initial matrix memory locations. So even though we transpose it, when we go to flatten it, it can't do the correct computations because the memory allocation isn't contiguous for the shape of the tensor. To fix this, we have to use the PyTorch contiguous operation to allocate the memory correctly for the transpose matrix. So very much like what the error told us to do. We're going to say PT transpose matrix, and then we use the .contiguous operation. We're going to assign that result to the Python variable PT contiguous transpose matrix. Now that we've gotten the memory to be contiguous, let's check to see if we can flatten the PyTorch tensor. So PT contiguous transpose matrix .view -1. Perfect. We were able to flatten that transpose matrix into a vector. And just to check, let's see if we can flatten our PT transpose matrix. So PT transpose matrix .view -1 gives us the same error. So what that means is that when we use the contiguous operation, it's not actually doing an in-place operation for the tensor that we are applying this operation to. It's taking that tensor and it's creating a new tensor, which we then assign to the Python variable. Perfect. We were able to use the PyTorch contiguous operation to move a PyTorch tensor's data to a contiguous chunk of memory so that we could operate on it with the PyTorch view operation.